Okay, welcome back. And so this afternoon, we'll start with a presentation about the perspective on the EIC, and then we'll have the student presentation. So if you would, make sure you upload those. And so we're all set.
Okay, very good. So you've heard a lot about the EIC, the science, theory, as well as experiment, the collider, the detector, the measurements. So we have started giving this lecture is somewhere in the middle of the school to give you a perspective on the historical evolution of the EIC. And the aim is to emphasize a few things. One, most importantly, that this project has evolved over 30 plus years. So these kind of things are long-term commitments by enormous number of scientists. And so if you thought that from some of the presentations that people are now working on it meant that we just started working on it 5 years ago when the long-range planning documents came out, et cetera, et cetera. No, we've been working on it for 30 years almost. The proof of which I'm going to show you in my presentation. I'm going to pick some slides from people, myself and some others who were giving in 2002 on the science of EIC and trying to make the case for it. The second thing, as I was talking to some of you in the evenings, that this is a place where you do not isolate yourself as being experimentalist or theorist. You will see that the whole evolution happened through tremendous communication among scientists of all kinds. So there is no, in QCD in my mind, there is no demarcation between experimentalists and theorists. I don't consider RIC to be complementary of, technology-wise is complementary to the EIC, but there is a fundamental connection that QCD is universal. It should be universal. Science is universal. Whether you study it within protons and protons on nucleus or electron on nucleus, we need to figure out that these are common themes that, we need to understand all of them. So with that introduction, let me just give you so I didn't, I scratched out the overview in my title, but call it from a dream to reality, which means that it was a simple idea that started some time ago, and then it sort of flourished into a real project over the 30 years. So this is the story of that evolution. So, what I'll tell you is that the collider, now from various talks that you heard, collider needs two rings, counterclockwise rings. And those rings carry the beam. The beam circulates in counterclockwise distance. The beam is actually a set of bunches, right? There's a series of bunches. It's not a continuous beam. It can be, but most often colliders have bunched beam. And then you need to synchronize them at the point of collision. Yeah. And that's when the collisions happen. But you don't always need a circular collider. So in fact, this electron-ion collider has gone through phases over time. The original idea was a ring-ring design where two rings were counter-rotating, beams in two rings were counter-rotating, and they would collide. Then for about 7 years, we gave up that idea and said, we can do better with a LINAC ring. LINAC is the linear collider or linear accelerator, which is an electron beam, which is a linear accelerated, and then hits at a tangent with the RIC ring. So that was the LINAC ring design. And about 10 years ago, we gave up on that and came back to ring because the accelerator physics had developed high enough to get the same parameters and get them cheaper. So we went back to that. So that's another lesson. Over 20 years, technology changes and emerges. The thing that you think today is going to be the most promising one might not be the one that you eventually build. Yeah. So we went from ring to LINAC ring to, again, ring. And these are main important documents that came through the life of electron-ion collider. I'll talk a little bit more about this. Just remember, there were three thresholds that we were looking at. The first meeting which the rig in mind as one of the beams for the electron ion collider happened on December 3rd and 4th in 1999. And I remember that day because December 3rd was also the day on which my daughter was born. So I organized the meeting, and then I missed that meeting. Then the first big meeting that happened was at Yale in 2000, April. So you can call this as a kickoff meeting for a ring design. And you can already see that that's the first default design that we had. It is 2 rings. In fact, we called it the 3-ring circus, because at that time we were planning to only add the electron ring to the existing ring tunnel and have collisions of hadron, nucleus in some regions, and then collide the electron in another region. So we thought, because it was, you remember, rig program started in 2001, and this was before that. So nobody in their right mind was thinking we'll get rid of the rig rings to put the electron beam. So that was the idea, that we will say, okay, we'll just add enough, there is enough space there, we'll add the electron ring and collide it at selected places. Not necessarily the Phoenix and star locations, but there are 6 or 4 other places that we could do it. Then the real evolution started around 2008. The idea came that instead of doing a ring design, do a single collision with a linac, a set of linacs that accelerate the beam and then collide them with one ring. We were told that the luminosity will be better, the quality of the beam will be better, etc., etc. And it was not that they were lying, they honestly believed, the accelerator physicists at that time felt that that was a better design. And if you want to know the details, I can talk about that later as to why simply a linac ring is a conceptually at least very difficult, very attractive, but difficult to build because of some technical needs. So we had this idea where we had, who amongst you goes to Jefferson Lab? Right? You know the CBAF? This looks like CBAF, right? There's 2 half accelerators, and then there is circulating arcs, and here is the collision. Yeah, so it's very similar to that. There was another one in which it was more traditional. So there was a linac here and a small ring, and that collides with a single part. Yeah, there was another version. And in 2014-15, we said, okay, this requires another 20 years of R&D, whereas the machine elements for ring had evolved over time from 2002 to 2014. Now we could build a ring faster and still achieve the luminosity that we aimed for, which is 10 to the 34 per second square per second per centimeter square. Remember, you heard it from the accelerator. So we'll get there. So so this is what looks like, almost close to that looks like today. So as I mentioned, this is not meant to be an overview of science, but it will come through. The science of the EIC has been covered in other lectures. These are about the origin, evolution of EIC based on some of the questions I heard from you in the evenings, in the last 2 evenings, or in the corridors. Yeah, so that's something that I started putting together. First, to remember, this is an international effort. It started internationally. However, the amazing thing that I find is that the basic questions we asked were asked by scientists in 1980s. One question was, where does the proton spin come from? The proton spin, we know spin is half h bar, yeah, in units. And we want to see how much of it comes from the quarks, how much it comes from the gluons, and is there anything else remaining? So in the first introductory physics lectures on the EIC, you already learned that over the last 50 years, we found that about 20%, 25% of the spin of the proton comes from the quarks, and another 20 to 30% comes from the gluon. So where is the rest of the quark spin coming from? And now we believe it comes from the orbital angular momentum, and that's something that we have not directly measured, but it is part of our understanding of the 3-dimensional structure of the proton. That is where that idea comes from. You also heard that the origin of mass is also not quite understood. We understand the masses of fundamental quarks, the bare quarks, they come from the Higgs mechanism. But if you add all the masses of those particles inside the proton, you get only 2% or so of the mass of the proton. So the rest of it has to come from the energy associated with the interaction, because the energy associated with the gluon interactions will simply E equal to mc squared creates the rest of the mass. Or you can think about it as the binding energy required that is lost to create the mass. Yeah. So that's something that we don't understand. That's something that we want to understand here. But it was really scientists from all continents were involved in exploration. And in my opinion, the experiment that was done at CERN in the 80s, which was a muon scattering on fixed target. And for the first time, a polarized proton target was inserted in it. And they discovered for the first time that the prevailing idea that the quarks carry all the spin of the proton was completely wrong. So that was a big shock. It was called the spin crisis by some of the senior scientists, and became a buzzword and became a New York Times and London Times news that there is a huge problem with this. It was not really a problem for experimentalists. It was a problem of the theory community because they believed that that's how the spin originated. So the model had to be changed. Yeah. And the second thing they did, the same experiment, they put nuclear targets and figured out that the parton distribution functions, as you and I know it, of a free proton were different than the ones in the proton that is sitting inside a large nucleus. So there is a nuclear impact effect that changes the parton distribution function. Yeah. So now you think about all the physics that you've learned about the EIC. We do two things. We do electron ion scattering or electron proton scattering. Everything that we are talking about originated in these two things that we learned that nuclei are different. Protons in nuclei are different. How are they different is something that we are trying to continuously go. And depending upon which energy scale that you explore, which X range you explore, you find new things. And that has continuously evolved along with the theoretical understanding. And now we are at a place where we cannot do better unless we go into these spaces of XQ squared, which have never been measured. And that's how you go and propose a new machine, a new facility, that none of the existing facilities can do this, hence we need this next. So at that point, there were few proposals. There were proposals to build a collider, 3 of them in Europe, one at Grenoble, which was a half-hearted thing, GSI in Germany. They really thought about building a collider at about 30 GeV center of mass. And some of us who came from CERN first went to DAISY because you heard in some of the lectures that Hera was an electron-proton collider at 300 GeV. So it was very obvious that you had the ring, you had the proton beam, you had a polarized electron beam. So you could just polarize the proton beam at Hera. Then you get first program that we're talking about now. And then if you could put in, instead of the proton, some nuclei, you have the electron nucleus collision. So some of us, including me, actually we moved to DAISY for 1 year to study that and see how that can be accomplished. We think still today, it could have been done. I still believe it can be done. But there was something else going on locally that they wanted a much, much bigger project. They wanted to extend the life of DAISY for 20 years, not for 2 or 3 years that I was proposing or some of us were proposing. And that's very natural. Any lab director, any large lab, they have to look at their future in that time scale. So they turned us down. Yeah. In the meanwhile, immediately following that, there were attempts here. The ERIC at Brookhaven, which is now realizing. But there was also an attempt at IUCF and Jefferson Lab, of course, much later. I'm missing MIT. MIT Bates. MIT had a small electron machine. And they planned, we want to extend the life of that. Let's put a small proton machine there. Something like what they had at Indiana University, about 3 GeV protons. So the total center of mass energy by S is equal to EP times 4 was of the order of 3 to 4 GeV, but in a collider mode. Yeah. The Indiana University said, oh, we have the proton machine, let's put the electron machine on there, electron beam on there. And they wanted a collider too, for the same reasons that we had done experiments there, but in the collider geometry. Eventually, EIC stood up as the unique one because the energies were higher and various other things that we'll talk about as a. But the point is that there were attempts everywhere. Ideas emerged from different directions and different motivations, but eventually we decided that the best way to do this was to come together. So here are the list of things that I just mentioned. From 1990 to 2000, we had an effort going on at HERA, and you can see I was involved at that point in workshops that were run by Albert Deruck and Klanner. That was regarding polarizing the proton beam at DAISY. And you'll see some familiar names here, additional EP theory support, and you'll see some plots that I found from my 2002 slides, who were working with us continuously to make the scientific case stronger to go in there. As experimentalists, we knew what the limitations of our acceptance were using a fixed target experiment. But we also need support from theory all the time to say, okay, what happens if you go in that region? What would you expect to see? And could we measure those things? And that's exactly what was supported by the theorists, which are shown here, both in the electron-proton direction as well as electron-nuclear direction. So those are people who you will see their names came up in the EIC context as well. Then there was, I mentioned to you, there was an effort to go to about 30 GeV center of mass at GSI. Indiana University was about 3 to 7 GeV, and eventually ERIC came out with the 100 GeV machine. And then we met at MIT under the leadership of Richard Miller, who said, look, we need to get one collider going. And we'll find the most versatile one, the most reliably constructible one. So we chose for a national laboratory. The science was broader than any of the smaller. And so that effort culminated finally in 2001 into this idea of the electron-ion collider. Early motivation. Let's see what drove us to that. So now you're completely aware of this simple diagram. Yes, deep inelastic scattering. You have an electron coming through or a muon, and then gets scattered. It exchanges a virtual particle, a photon or a W or Z, and then you have a momentum exchange with the proton. The wavelength of this, as long as it's small, that means the momentum is very large. You look inside the proton, that becomes deep inelastic, right? Otherwise, it's an elastic scattering. You don't see the internal structure otherwise. Yes? I want to see yes on your faces. Yes? You're with me? Yes? The wavelength of that has to be smaller than the size of the proton. You look inside the proton, right? So that's why you need a certain amount of minimum energy to look inside, to make it sure that you are looking inside the proton. And then this momentum will push some of the quarks, what we call current jets, and then the remnant goes out there. And experimentally, the accelerator provides us these two, and experimentally we start looking for these. And traditionally, we only looked for there. Because if you have a fixed target experiment, and typically a solid state target existed, and you hit something very hard, this particle does come out. But the target hits the next nucleus or next hard thing in the, it's a fixed target. So it's very difficult to see that in fixed target experiment. So that's something that you should. Whereas in the collider, it's a gas of nucleus and a gas of electron. They're just passing through each other. So if you hit it, not only you see the current jet, but you also see the target fragment going forward. So if you really want to study the full geometry and full study of interactions between And amongst the particles that come out in the target fragment and the jet fragment, collider is a very, very good idea. Yeah. And I'll give you another way of looking at it. This method is very powerful. It has many Nobel Prizes, as you saw in the first day lectures. Discovery of quarks, the spin crisis, the LMC, the nuclear strangeness effect. But there's one more very important thing that people have to understand why this method is really, really special. So here is the same diagram, same thing, but I have now tried to explain to you what that means in real numbers. So the Q squared is the momentum transfer here. That is, if you solve for these four vectors, comes out to be E times E prime minus 1 minus cosine of the theta prime, where cosine of the theta prime is right here, the angle with which the electron beam changed its direction. The initial energy is very well known because the accelerated energy is known. It's better than 0.1%. You build the collider, the detector, the E prime, and build the calorimeter based on how much money you have. Right? Or you can invert that. You say what physics you want to do, what the resolution is needed, and then you design the calorimeter accordingly. Yes? So now you know, just from measuring the scattered electron energy, exactly what happens to the Q squared. So that momentum is very well precisely known in deep inelastic scattering. The Y, the inelasticity, if you reduce these four vector, comes out to be amazingly, again, a function of the same three. And then the X Bjorken, you can again solve for it. It also comes out to be a function of theta, E prime, and E. Do you see the importance of this? Because you know the initial energy, because the electron is the unbreakable, powerful probe here, you are able to calculate it by just measuring the scattered electron. And if you have a proton in this case, which is used often as a probe in proton nucleus collisions to study the nucleus, or proton-proton collision, you never have that accuracy because you don't know which quark with what energy, what fraction of the energy actually collided. You can deduce it later from physics, looking at the final states, dyne jets, whatever that you're looking at. But here it's an over-constrained system. You could do the same thing that I just described to you using the final states, but you could also do this using the initial. And that is why it is unique. It's really important to understand that. That's why electron or muon scattering is special. Okay, that's why deep inelastic scattering is special. Okay, so here is again motivation. I think I mentioned to you in a fixed target experiment, here is the target, and the muon beam or the electron beam comes from this side and hits everything. The nuclear fragment do not come out of the target volume, most likely, most often. And if they do come out, they've already lost a lot of energy by moving through the solid state target or liquid target. Yeah. So you never know what happened in the first place. Yeah. And then there is the scattered muon or the electron, but you also are creating a lot of particles in the collision. Most often pions and kaons. They have a tendency to decay into muons and electrons. So it's very difficult to identify. I mean, it can be done. We do it routinely, but it's difficult to find which was the scattered muon and which are the muons that are coming from the decay of the pions. If you make a mistake there, you have the wrong kinematics. Yes? Now, let's go to the other direction. Now, let's see in a collider mode, the proton beam is coming or nuclear beam is coming from here. The electron beam is coming from here. The collision happens. Electron goes that direction. Nuclear fragments go there. Ions and kaons go in the center. Everything that you want to study are well separated by the geometry, based purely on the energy balance in the collision. Yes? You see, experimenter's life is easier if you do this. It makes the accelerator physicist's life more difficult, but the experimenter's life is easier. Because now you know that the electron is predominantly going in that direction. you know higher resolution is needed in that direction. Of course, depending upon the kinematics, these things can change, and they do change. But predominantly, you can separate them very well. Yeah. So that is one of the reasons why collider geometry is easier for experimental. So here is a slide I took directly from a talk that I gave at Brookhaven in 2002. One of the other things that I want to emphasize, that as a function of time, to make the case for an experiment or a facility is becoming more and more difficult. That's an unfortunate state. So you will have more difficulty than we had. But I can tell you that I talked to my predecessors, senior people, and their proposals for experiments typically were half a page. And one particular thing that I remember, the person who first invented and demonstrated a polarized electron beam was my mentor at Yale. And I asked him, so why did you first build the polarized electron beam? And he said, I'll show you the proposal. This was in 1962 that he built first, before the quarks were known. So it was not like he was trying to study the electron scattering or something, nothing. So I asked him, why did you do this? So he showed me gave me a paper. And I said, I just don't want the abstract. I want the full paper. He said, that is the full paper. It was like 6 lines. They said, we have the ability to do this with the strained gallium arsenide crystals. And we shine laser on it. We think we can produce polarized electrons. And they might be interesting for future physics studies. That's essentially what he said in 6 or 8 lines. And he got $350,000 in 1962 to demonstrate that. And he eventually did, but giving you now you're going to see a lot of paper that we wrote for this collider over the last 30 years. So if you want to propose a new collider for the future or some experiment, be ready. It's coming exponentially increasing. Anyhow, so and this is also a example. Now we have to do a lot of simulations. Some people are involved with the EPIC detector here or S-Phoenix detector. You know how hard you work to create those plots that went into the yellow report, right? But we started with simple things. Low X surprises. We just listed, these are the surprises that people have seen by going to successively lower and lower value of X in X Bjorkane. And we have always learned new things. Yeah, that's a very high level statement to make. If I just give you that now, I don't think that will work, but at least people were listening to us at that point. Here's another one. Any polarized experiment have fundamentally changed the way we think in physics. So here are some surprises over the last century, where spin was one of the variables in the experimental control that allowed us to discover something completely new that we didn't know. And these are all in the undergraduate textbooks now. That's the big deal, right? And we are now proposing a polarized experiment with protons and neutrons and light nuclei. So what you guys should be aiming to do is to do that work and appear in undergraduate workshop schools, textbooks. That's the criteria. Not just published papers, but these are the high-level things that you will probably potentially be able to do. Here's a plot I found from 1995, and here's some explanation is needed. So you understand this plot. This is the X Bjorkane versus the Q squared. And you saw previously in other talks, this kind of a plot, right? Remember? Yes? And you saw that the collider takes you to lower X and higher Q squared because the S is very large. Yes? S is equal to 4 times EPEE. S is large, and that's also equal to Q squared SY. And so the higher the center of mass energy of the machine, you go from here to that. So here are all the world's fixed target experiments with electron scattering. Yes. Then here are the experiments with muon scattering. Muons can be accelerated to slightly higher energy. Why?
Radiation.
For synchrotron radiation. Yes. I asked the same question on the first day, remember? I am consistent, right? So because the muon mass is higher, the synchrotron radiation is lower. Yes, and that means that the energy you pump into the electron muon beam is retained more. And if it retains more, then the same energy, you put in some energy in both electron and muon beam, the muon beam will maintain some energy better. And that's why muon beams can go to higher energies, and you can do fixed target experiments with them. Yeah, so that's what we did, and that was the NMC experiment I mentioned to you at CERN was this kind of experiment. But now we realize that that's not good enough. We have to go further in the low X and high Q squared region. One of the things that we measured was the spin structure of the proton. And you now know what G1 spin structure is, right? G1 spin structure. It's the sum of the spins contributing from all the quarks. Okay? If you didn't have an introduction to F2 yet? F2 and spin, no? Oh, how come? I thought they would speak about that in the first lecture. Okay, so it's the sum of the quark spin contribution to the proton spin, and that is what essentially G1 spin structure is. And we had measured this like that at the experiment at CERN, and we didn't know what QCD could tell us about. So we would take the prevalent extrapolation and extrapolate that function using these 3 points to say, as you go to smaller and smaller x to 0, essentially, if you wanted to understand the area under this curve, you at least learned about Bjorkine sum rule and Ellis-Jaffe sum rule, right? In Sturman's lecture, no? Yeah, spin rules. Yes. Okay. So remember, we wanted to calculate the area under the curve for the proton and for the neutron. But we only stopped the measurement here. So how do you do the integral? So we took the prevalent idea, something called Regge extrapolation, that says it should be constant maximum. So all calculations that were done until that time assumed that flat line. But at that time in 1996, 97, we started working with this group here. And this guy is still here. He's in this room here. And they did the first and next to leading order calculation of the G1 spin structure function. And their paper said, here is the QCD extrapolation at NLO. And that was a big surprise to everyone, that the G1 spin structure function drops down like this. And it has very important implications for the structure of the proton, how much gluon it carries, gluon spin, et cetera, et cetera. But there was no way to go here other than to go in this region. And we had no experimental way of doing it. And this was the actual origin, at least in my mind, to go to a collider, at a high energy collider. And that was something that we discussed starting at that point. And that evolved into the polarized HERA program, which was summarized in the 1999. This was a document from February 98, 99. And you saw the importance of this curve was so much that the workshop decided to take that curve to be the headline, the front page of this. There were many, many things that I'll talk a little bit later about, but this was the one that was simplest to take as a shocking discrepancy of what people were doing at the time to what the NLO calculations were telling us. And this is an example of the same. This is the same curve, but now I have integrated over x. So x times this curve looks like that. So you want this curve, but then because it goes negative, you want to subtract a little bit part to get to the first moment of that G1 spin structure function. Yeah, and that is what creates the difference. So you can see the extrapolation using the QCD was very different than the one that Regge extrapolations were telling you to take. And that really made the case, or started making the case in many people's mind that, okay, we need to go in that direction. What else is wrong with QCD, or what else is wrong with our assumptions in that region. That's how it whole thing started. Another way of looking at it is that here again, this is Q squared, and this is unpolarized structure function, F2, measured over very wide range in X. So this is 10 to 3 times 10 to the minus 5. So it's really somewhere here. And here it is about 0.65, which is right there. But this is the unpolarized structure functions, F2. And you see that over the next 10 years or so, Hera measured these unpolarized. Remember, Hera had unpolarized protons. And they measured this. So we could have, in principle, if we had polarized protons, we could have measured G1 spin structure function exactly where I wanted to, or where we wanted to. But there was no polarized proton. And so we could only were limited to this area here. And to date, this is where the state is, because there's never been a measurement in the collider since 1998 to make that measurement possible. Yeah. So here is another thing. You want to propose something, you propose it uniquely, in the sense that there is no other machine in the world that even today is even planning to make such measurements with polarized protons. The only machine in the world is the RIC so far. And then since we are using the RIC beam to do the collisions, we have ERIC or EIC. Here is again the nuclear beams in Hera. We made a case for nuclear beams. This is the kind of accuracy with which we thought we would do if we had just nuclei in Hera, and there were people working on such parallel collision proposals. One of the things that Hera management did was they told us, you either get polarized protons or you get nuclei, which means that these communities will not, they get 3 years of operation and you get either this or that. So the community was at odds with each other. We never got together. Adding to that, some of these people were very close to some of the very prominent physicists in the world. I'm going to show you an interesting thing. This is a letter. So McLaren was, let's see, Strickman, these are the people who were promoting the nuclei. And they said, how can we make sure that DAISY management knows this is really important? So they went to Mr. Bjorkane, same one as I'll be talking about, Bjorkane's sum rule, right? Bjorkane or Bjorkane X. And they said, what do you think about this nuclear program at Hera? And he said, that's a great idea. We absolutely need to do it. Meaning EA scattering. And they said, would you be willing to write a letter? And he wrote a beautiful letter in support of the EA program. And that's the letter I found in Mark Strickman, one of my colleagues now, his office, he kindly faxed that to me. So that's the letter. It says that this is an important program for QCD, EA. And then we were sitting on the other side of the fence, thinking, my God, we lost. Bjorkane writes EA is great. What do we do? So my mentor at that point knew Bjorkane very well, and he was pushing for the polarized proton. He said, let me call him. So he called him and said, do you know that there is also a possibility of doing electron-proton scattering with polarization? Oh, that would be great too. So he said, can you write a letter? And he did. He did write the letter. Unfortunately, it's in the archives of my mentor's collections. I don't have it yet, but I'm going to eventually get that. He wrote a very similar letter saying that this would be a great program too. So, we just neutralized all these Bjorkane letters. But this was a learning experience for me, because he was not told in the first instance, maybe he didn't ask, or maybe he didn't appreciate that the two programs in parallel. And he didn't have a preference over one another, but he was presented, is it good? And he said, that's great. So, okay, can you write a letter? And we repeated that, and all worked out negatively for all, right? Because they didn't go for that. Okay, they had other things in mind. And so we sailed. So most of the people who were keenly doing things or thinking about the polarized EP and EA in Europe, we all sailed to the new land where RIC was just about being built. We will have nuclei, and we were supposed to have polarized protons. That's the only place in the world that it was being planned. Yeah, because Daisy rejected us, we all came here. And this was where we started again. This is September 2002. ERIC was the term coined by my friend Raju Venugopalan. He's a scientist at Brookhaven, also a joint faculty here. And we started working out a first science case of the electron ion collider and you can see that the plots are very similar now. We knew so this is the Hera limit, this is the EIC limit. It can cover the lower energy fixed target experiments, but still go into new regimes here, which is where we wanted to see, for example, the dipping down of the G1 spin structure that I showed you before, and measure F2s and measure many other things that you need for TMDs and GPDs. Now you know that. It's interesting, if you look at those papers in 2000, until about 2005, there is absolutely no mention of TMD. There is no mention of GPD. It was all inclusive measurements, mostly, and some semi-inclusive physics. Why? Because we did not know if these things existed. We did not know how to incorporate them into QCD. There were some very basic ideas, but nothing that we could use for making any case or not making the case. So one of the things that I'm often asked, aren't you unhappy that the EIC took this 30 years? And I don't feel unhappy because I think if we were too fast, and if we actually had run and built the polarized proton at Daisy, with the luminosities that they had, which is like 1,000 times smaller than what we can now build, with the range of nuclei they would give us, I think it would have been not a great program that we're going to have eventually. So the evolution of theory over the last 20 years was extremely important. The evolution of accelerator technology that can get us to 1,000 times luminosity than the previous collider, and the technology for detectors to accept all of that physics has also grown. So in my opinion, I'm not unhappy about it. I think the program is much stronger now. Could have done it faster and okay, but then building the second collider would have been much, much more difficult. First collider is the right thing to do. Right? So this comes back here. And this was a list, the spin structure of the proton and the neutron at low X, Bjorkane sum rule, gluon's contribution to proton spin. These are simple things that we can measure with inclusive physics. Those made all the highlights. And look at this, DVCS, transversity. This appeared or in names, in simple things, because we didn't know how to even measure it or whether we would be able to measure it. Because we didn't know how large these effects were going to be. They had not been studied in great detail in any place. Yeah. So that would have been the program. For the EA, there was really one thing, and that I think you have heard from various speakers, is that the gluon saturation was the main attraction. It still was then as well. And was this discussed in any lecture here? What is the origin of gluon saturation? No? Physical origin? Okay, let me tell you. So you know that let me see if I have a. Okay.
We'll have small X next week. Matt will do that.
Matt will do that. So what you will see is the unpolarized parton distribution functions, which are determined extracted from data using the CTEC methods or any other global analysis methods. That tells you one thing. One thing that is that the gluon distribution rises at low X. Yeah, it rises and it doesn't seem to saturate. It keeps on going based on the current measurement, all the way to about 10 to the minus 5, which is very strange. Because what that means is that if you go and reduce improve your resolution of looking inside the proton, that means you start looking at smaller and smaller momenta, the gluon number density keeps on growing. And that's the shape currently in the proton looks like it is going infinite. And we physicists, experimentalists especially, do not like infinity in our measurements, right? So something else must be going on. So the simple explanation of saturation that you can relate to, I'm sure, is the following. Look, the gluon has color charge, right? Unlike the photon, which doesn't have an electric charge. So the photon cannot split into two photons on its own, yeah? Or photon cannot interact with another photon on its, simply. The gluon can do that, which means that as long as the energy is conserved and the momentum is conserved, a gluon can split into a different colored gluon. Two, let's say. Those two can split into two more, each 4. 4 become 8, 8 becomes 16, and keeps on going. Those interactions can happen. In fact, if you look at the Nobel Prize lecture by Frank Wilczek in 2004, he talks about this particular phenomenon. He says that a color charge in isolation results in a colored thundercloud. Yes? And the key word there is isolation. It really doesn't happen in nature because there is no color charge in isolation. It's always within the proton or a nucleus, yeah? So, because it is confined. So now you look at the proton and you have this gluon that is splitting, and that is splitting into 4 and 8 and whatever. Its proton is getting very crowded. So this rise that you see in the number density for lower and lower momentum is coming from there because of the color charge. However, as long as you are confined, there's going to be a crowd of gluons. And you're going to start bumping into each other, which means that the merging probability also increases. Yes? You just don't have production, but also recombination of it. And at some point, the density is high enough that the two will become equal. And at that point, the gluon distribution should actually change the shape, make it more flat, and eventually completely flat. And an experimental signature is to measure that F2 structure function and from there extract that gluon distribution and see if it really does flatten out or flatten. That is one of the main goals of the electron ion collider, to see that saturation. But we don't see it in the proton even at 300 GeV, and you know that the EIC is about 100 GeV or 140 GeV. The trick is to use nuclei. You get 200 extra protons, 200 protons in a nucleus or 100 protons and neutrons. They're all squeezed together to enhance the parton density, and then we measure it. We're not looking for energy, we're looking for the high density of parton. Yes? And so that's the trick that we use. So that's why nuclei are important to do this. So those were the sort of the pillars of science. And in 2002, we first presented it in the US in the Nuclear Science Advisory Committee Long Range Planning. So in the US, the process is that the idea is there is a review of US nuclear science internally and also with respect to all the rest of the science that is going on around the world. That happens every 5 to 7 years. And the planning is for 10 years. And then every 5, 7 years we meet, we see what we have accomplished, what are the more important questions that has emerged in those 5 to 7 years, and we propose the science of that. So we had to go through this because it's a new collider, new machine. So we had to present it to the NSAC, and that's what we did. And eventually, in 2002 long range plan, the first time we presented, they said there's a strong consensus among nuclear scientists to pursue research and development. This didn't say if you're ready, and we were not ready, but the idea existed. So they started giving us a little bit of money to develop the theory, the detector, and mainly the accelerator, because that's going to be the most demanding part. We understood it right from the beginning. So that's what the first recommendation came through. The NSAC long-range plan, finally, in 7, so that developed into a more mature case by 2007. We had another recommendation that it says, recommendation allocation of resources to develop the accelerator and detector technology. By this time, they acknowledge the theory is developed enough to make the case. We think that that is really important. That should continue, but now we need real money to do the accelerator development and realize it. Yeah. Remember, at this point, we were only talking about the ring design. And at that point, the idea of Linac ring came in. And they said, we can give you 100 times better performance than the ring. Then to the 32 was the ring design, based on which we had made this case. And the Linac ring folks came in and said, we can give you 100 times better. We can get to 10 to the 34. And so everyone said, oh, let's look into this. And it is true from the accelerator side point of view, to have a new technology, an energy recovery Linac, which is a novel accelerator tool, it's important for the world in the future. And it can only be done at major national labs. So if the national lab says we want to invest in this, we should encourage that. So that's when the first time we went in the direction of the Linac ring. At that time, the estimated time for R&D was estimated to be about 4 years. And so we reviewed it again in 2011, just before the next long-range plan, and realized dramatically that they were lagging behind in R&D. But at that time, we also learned that the older ideas of Linac ring had developed far enough to go back to it. So we made the final case in 2015 using that. And by that time, we had developed concepts for detectors. There were 4 ideas floating. One came from Jefferson Lab, one came from people at Brookhaven. Then there was led by Argonne National Lab, and there was another one from Brookhaven. I mean, this is not just labs creating it, but centered around the lab activities. There are people from universities working on it, but there were 4 to start with. And by this time, there were 2 proposals for the collider. So here is the ERIC proposal at Brookhaven, which you have seen multiple times in this school, but there was a competing proposal at that time for Jefferson Lab. And this is the familiar CBAF. This is the all D, all ABC, all that exists. And they were proposing that we'll extract the electron beam and put it into a new tunnel to be built right next to that on the facility, on the JLab facility, and have collisions there. Yeah. I will not go into currently why they look like a bow tie. That we can talk about at beer or even before if you have questions. But basically to keep the polarization up, like what we have at RIC, there was an ingenious idea as to how we can do this by using a bow tie shape. But you can see that the machine got defined during this time. It says that we need polarized beams of electron, proton, deuteron, and helium at least. We need a variable center of mass energy. So we need an energy of the electron beam to be variable as well. We wanted the luminosity about 100 to 1,000 times that of Hera, and variable center of mass that results from the various energies. Wide range in nuclei, etc., etc. And it would be the first polarized collider in the world. It still will be. It will be the first electron nucleus collider. It still will be when it gets built. And funding-wise, this is a very important statement. One of the RIC exists, the tunnel exists. If you wanted to build in a new facility, to build the tunnel, it takes $2.2 billion. We estimated that recently. So the replacement cost of all the injectors, the sources, the RIC tunnel, the AGS, everything today, if you wanted to build it today, it would be $2.2 billion. So once we told the world that we can use the same tunnel, that was a direct saving coming from using all the investments that already were made. The science was summarized in something called the white paper. It looks blue, but this is where the whole science is based on. Just to give you an idea as to how much precision it can bring, this is so here's the proton spin puzzle. This is the spin carried by the quarks. This is the spin carried by the gluons, and these are the components that are associated with the angular momentum of the quarks and the gluons respectively. And what is plotted here is the knowledge of this delta sigma, that is the quark spin on the x-axis and gluon spin on the y-axis. And at that time, the uncertainty in these plots were like this. And the estimates of what the EIC could do were studied through simulations. And so these are the islands that that's the precision you could get. Yeah. And once you get that precision, then just by putting these numbers here, you can start estimating what LQ and LG would be. That's somewhat cheating. This is just subtracting the two from there. There's a direct way of measuring it that you probably learned through deeply virtual Compton scattering in one of the lectures. But that would be the first attempt, first start with high precision delta sigma, meaning the quark spin, G1 spin structure, and delta G. Yeah, we can already start getting a very good picture as to how much of those things are going on. Now, there is also effort simultaneously on lattice that has started to calculate any of these, all of these components separately that has evolved over the last 5 to 7 years. So those are important, and eventually we want to compare and contrast with those measurements. Here is that gluon distribution that I've mentioned to you before. This is what comes out of current knowledge of the deep inelastic scattering that comes from Hera and mostly Hera, but also from others. And I already mentioned that the low X rise comes from this kind of splitting, continuous splitting of gluons in 2, 2 into 4, 4 into 8. And then when it becomes clear that the density is high enough inside the proton, this recombination process also takes over. And at some point, they should just. And I think so this is where the log X or 1 over energy and resolution is. And this is where the high X proton is like the valence quarks, and you go down in low X. We're asking whether there is a transition between normal matter to saturated protonic matter. And that would be signaled by a change in the shape of that gluon distribution. Yeah? Because at low X, there is really the gluon dominates the field. Yeah? And instead of doing the proton, we would do this by the nucleus, because proton is not going to, we know proton doesn't saturate at that. I mean, the partons and protons don't seem to saturate. We already know that from Hera. So we need something else, and that's the nucleus. That's the role of the nucleus. So those were the summary bullets that I think you've seen in Rosie's talk in the first day, the first lecture actually. Where is the proton spin coming from? Where is the mass coming from? What happens to color charge as it passes through the nucleus? What are the interactions here? How does it know how to convert into a pion or a kaon and neutralize its color component? So that's an important thing about confinement, color confinement. This is the kind of study you want to do. And last but not the least, what happens in nuclei at high density. So all of that came through this kind of studies. Here is another way of looking at it. You have a parton density going up here. That's 1 over X going there. And QCD Q squared, the resolution is on the y-axis. And there is some transition. This is a schematic diagram where there is a transition from non-perturbative to perturbative regime. Yeah. And electron ion collider, because it can do the scattering in a controlled way, and you can isolate events at different Q squared and different X, you're able to select event samples after you do the analysis from any of these regimes. So to high to low X, to low Q squared to high Q squared. And you know that perturbative QCD works very well at the highest Q squared. We know that. We can do weakly correlated quarks and gluons. And then the hadron structure is something that is a mystery because of the non-perturbative effects that we can't calculate, but you guys are calculating using lattice and other things. And then there are various phases or states of matter in confinement and that we want to study. And finally, if we go to high enough parton density and can remain in the perturbative regime to study this high density gluonic matter, which has been promoted or proposed as a consequence of this color interaction. It has to happen at some place, but it does it happen in the place where we want to study? And what properties does it carry? So that all becomes the case for the, and this is again going into a no man's land or no woman's land or no person's land. Here is the data from the fixed target experiment. These are now the kinematic limits of a 65 GeV collider, center of mass energy, and the highest the EIC can reach is 140. So you can see that we are really going into regimes where we have never made measurements. And the same thing For the nuclei, these are the fixed target nuclear deep inelastic scattering experiments. And this is where the EIC will make measurements. Yeah. Those who are doing TMD studies, you appreciate the value of studying not just the TMDs, but you probably are thinking about evolution of these structure functions. G1s, of course, inclusive. The TMD, you hear it now or more often. How do they evolve as a function of Q squared? And that's something that is essential. And you can study that because of the broad range in Q squared the EIC gives you, a possibility of measuring over 2 orders of magnitude. No other experiment can do that because no other experiment has the large S or large Q squared reach. Yeah, fixed target experiments are very small and localized compared to the collider. So here is the summary of the science at center of mass energy on the x-axis and the luminosity on the y-axis. Yeah, so you get the feel for if I reach the collider reaches the 10 to the 32 luminosity, which is what we were thinking about in the first place, then most of the science that we think about is study of the nucleus as well as the study of the dense nuclear objects at highest energy. That we can start and we can do. If you give me a 10 times more, now you can start studying the spin correlations, which means now the data have collisions with this kind of collision, that kind of spin oriented. You flip the spin, you study transfer spin in this way, that way, that way. So now you split the data into much smaller parts. And that's why you need the larger luminosity, because you need statistically significant samples for each one of those states. Yeah, and that's what tells you that you have to go to study spin and structure function about 10 times, 5 to 10 times larger than the simple inclusive nuclear study. And then when you go to tomography, when you want to do GPDs and TMDs together and understand the three-dimensional structure, there you cut as you know, there are more variables to cut the data into. Yes, there's impact parameter, there is KT, there is X, all of these things come in 2 dimensions. So essentially you're making measurements of 5, 6-dimensional objects. And that's why you need even higher luminosity. And that's why that is the most demanding in terms of the luminosity. And that's why it never appeared in the early parts of our science case, because we never dreamt of reaching 10 to the 34. We said 33 would be at the most possible. We are now promoting that on day 1, we will reach 5 10 to the 32, and day 5 will reach 33. Yeah, and then it will evolve into something even better as we go forward. All right, so this is a big deal. So we made the case, people voted yes, and then we had to write the recommendation. So there is a person here, Dave Herzog, who was the chair of the committee, and you see me, quite young, I had a lot of hair, and yeah, they were all black, or almost. This was in 2015, April 16th, yes. And it was funny, the chair of the committee of the whole process, Don Giesemann, took this picture and said some felt the need to invoke higher powers to get the recommendation right. We were both typing, and as hundreds of people sitting in front of us, it was a jarring thing because everyone was saying, no, you change that, no, you change that. So that's how it happened. So this picture comes into picture. Anyway, this is the recommendation that was written. We recommend the high energy, luminosity, polarized electron-ion collider as the highest priority for new facility construction after the completion of FRIB. I don't know whether you know what FRIB is. FRIB is a machine that was just completed in May 2022 of construction at Michigan State University. It is the facility for radioactive isotope beams, FRIB. It does studies the nuclear astrophysics machine, basically. Yeah. So that was being constructed at that time. Now I'm telling you that it stopped construction into 2022 in time exactly. And according to this recommendation, EIC should start construction afterwards. And that's exactly what we are doing now. So again, the collider got a lot of press immediately after it was approved. You can see various news bulletins. One important step for any, and this is for information, is that when nuclear scientists or any scientists, we vote for it, right? It's our future. But that doesn't mean that we get the money to build it. scientific community in the US has to generally bless it. So when the government needs such a blessing, they go to an august group of people called the National Academy of Sciences. There are people from all fields in science and social sciences on it. There are chemists, there are medical scientists, there are physicists, nuclear, particle, atomic, everyone in there. And they form a committee. They say, these people are asking for $3 billion. Should the government spend the $3 billion? Then we were asked to present the case to that broad an audience, to convince a medical doctor why this is important. Yeah. And that's an important thing. It's really a valuable thing to do. And I recommend highly. I was talking to some of the small groups that you have to convince these ideas to a high school student. Remember we talked about this? When you talk to a senator, you need to go to that level, right? And it's not bad. It's not bad. The senator is not a scientist. But if he or she can get convinced, then you have a huge supporter, yeah, with lots of resources. So don't underestimate the outreach in any of the scientific fields. What you do now, working with high school students or college undergraduate students, very important. Yeah, very important. So just not for science, but some of you will become professors and teaching training. Yeah, that's something that you will need to do. Anyhow, we went to National Academy and they said that the science is compelling, it's fundamental and timely. So compelling and fundamental means they valued the science at the highest level. That's all they can do. They cannot say, okay, go ahead and build it. That's not their authority. What they were asked to do is to evaluate the science and tell us whether it is worth going forward. DOE takes the decision to go forward, but this committee just says, so that's what they said. And timely is an important word. The technology is ready or not. You can't give them money if the technology is not ready, either the machine or the detector. Third thing is important, and that brings me again to the theory part. If you make these precise measurements with this machine, and if I give it to Stefano Ford and say, hey, here's the machine, here's the data. And Stefano said, I have no theory that I can now put this in and really understand what's going on behind it. Then all that money is not useful, right? So theory has to develop together with experiment. And that was what was evaluated in that timely as well. If we had data on GPDs, if we had BVCS with that precision, or TMDs, or low X physics, can it be used to meaningfully interpret what's going on in QCD? For that, the evolution of theory is very, very important. Yeah. So that's why this synergy between experiment and theory, don't underestimate it. Just because you are experimentalists and you're theorists, do not ignore talking to each other. Really important lesson. Yeah. Okay, and then we were lucky enough in January 2020, the Department of Energy selected Brookhaven Lab to host the majority to the collider, along with Jefferson Lab as a partner. Since then, we have been working together. This is the story that has brought us to the current state. You can see with some little variation, this is how the collider looks now. We use the injectors system that already existed. We use the rig tunnel. We use one of the beams, the yellow beam in the rig tunnel. It goes this way. We have an injector for electron that comes through. Electrons go in that direction, yellow beam, right? And then we have a collision at the IR 6 o'clock region, which has become the primary collision point now, where the EPIC detector is being built. And in future, we are making sure that there is space and ability to have one more collision at 8 o'clock region, which is currently the home of S-Phoenix detector. So those of you are involved in S-Phoenix, we have plans to use that after S-Phoenix for a second detector. Okay, and I think those two will make the facility complete, in my opinion, because there is ability to control, to collide without tremendous loss of efficiency for operation. You can't imagine four. You can't imagine four, and for a simple reason. You have very intense beam of proton and a very intense beam of electron to get to the highest luminosity, 10 to the 34. Yes? What happens when one beam passes through the other? What interactions happen? Electrostatic, Magnetic, yes. So if you have a very intense beam, the sharper the beam and it passes through the other one, it destroys the other beam. So after the collision, and remember in the ring, the same bunch is colliding with the same bunch for 8 hours. Yes, so over time, these bunches become thicker and broader as they're passing through, which means that at some point, the effective luminosity drops. Remember the word luminosity from the accelerator lecture? So that means that you don't have enough collisions anymore per unit time. And then you're spending $500,000 per week of operation. It's not worth it, right? Then you have to dump the beam and fill it up again with highest luminosity and we go down like that. If you have a third collision point, we are already at something called the beam-beam limit, where these beam-beam interactions are limiting us. If you have the third one, then the drop will be much faster. If you have the fourth one, it will be even further. Then we won't be able to run the machine. And just to tell you, there has never been a machine in the world that has come to a beam-beam limit. We are now hitting physics limits. Yeah. Rick never came to it. We had 4 collisions in collision points. LHC has 4 collision points. Yeah. This is the first time accelerator physicists are hitting a physical limit that comes from fundamental physics, electrostatic charges of protons and electrons or nuclei. And that is why to overcome that somehow using some modern techniques and tools is what attracts the best of the accelerator physicists to this project. One of the complex problems, this is only one of them, but this is what we are dealing with. It's really at the forefront of accelerator technology. Then there was 3 proposals for the collider detectors. One was based completely new, Athena, in December 21, that said, okay, if we had no other constraints, let's see how we can build this. And that's what the proposal came out to be. Then there was something that said, let's start with the S-Phoenix magnet and build a collider detector around that magnet. It exists, it's operational. We'll just make it asymmetric by putting, because, currently they're doing gold-gold collisions or proton-proton collisions. What we want is electron nucleus. That means you need one side to have all hadronic measurements, the other side to have all electromagnetic measurements. Let's make it asymmetric. And that's what they succeeded in doing on the right-hand side. And on the third one, they said, we want to shrink the detector, make it very small, use the highest level of technology, most precise. As a joke, but it actually is true. If you compare the costs of detectors around the world, collider detectors that have been built, yeah, they come dangerously close to the cost of beef sirloin in the similar weight. You take 1 ton of, if this is 50 tons, take the best beef, 50 tons of base beef, that comes to almost the same, between 10%. And Bill Wright has a plot of this from Tristan all the way to Hera. And it comes within 10%. So you can estimate. So this collaboration said, we'll build a small one, but high resolution, because the weight will be lower and they wanted to reduce the cost. They came out actually half the cost of the rest of the detector, but they were not strong enough in collaboration. So they got dropped out. But my hope is that they will come back and build the second detector in the future. Among these 2, they combined ideas. They chose HA as originally an idea, but said merge the ideas from Athena and form a new detector. And that's what got built or selected as a hybrid between the first and the third, which is now called the EPIC detector. Yeah, I'll not go through it because you had 2 lectures on it, right? So I just want to say that came from 2 detectors. This is how it looks like in 3 dimensions with various technologies that came through, acceptances, and all the others. This is a very large international effort. Even the detector has about, I don't know, you see all the flags there. So there is not a single country that dominates. Even the United States doesn't dominate. they're also spread into all these subsystems. So this is an international effort. It is truly international in many ways. Monies have come already promised from UK. People are working on significant, I think we got about $85 million from UK, expecting about 60 million each from Italy and France. Japan just promised $30 million. CERN is contributing eventually to technologies which are very critical for LHC in the future, LHC++ and their FCC. We see that this is a place where they can try out all these things, so they're involved. And then Korea, India, other, they are also deciding on this to join in. I think we have done this. Here is the user group. I told you how many people are involved. I think 1,500 plus PhDs from all over the world. And I want to circle back to the first comment that I made. The first slide I told you that this is because the scientists from all over the world face the same technical or physical problem. To ask questions, what happens to the proton? Where does it come from? Those questions are universal. They were faced in Japan, they were faced in Europe, they were faced in the United States. All of these people are now coming to realize that this is a machine where this gets solved. And you can see the distribution of that. We have the first Australian. The two, yes. This is Adelaide, right? Yeah, you're welcome. If you have a collider, you can do many other things, and I'm not going to go into this. So those three things that I mentioned to you as became the main pillars of science. That's not the only thing you can do, but those were the three things that made the case for it. There are lots of things that people are interested in high energy that you can do. You can study various things of precision, parton distribution functions, unpolarized and polarized. That might be needed to improve understanding of physics beyond the standard model once you have an LHC luminosity upgrade. If you want to really understand if there is physics beyond the standard model, it's at high X and high Q squared. And the uncertainty that comes from QCD for the parton distribution function, the gluon distribution, for example, is the limiting factor of that extraction once the LHC luminosity goes up. So if you want to have a better measurement, we will give you 5 to 10 times better than Hera, which is currently the limiting factor. Yeah. So those are the kind of things that help not just the nuclear science, but particle physics. Heavy quark studies with spin with 100 times larger luminosity than Hera. What that will give, you can tell us. Something that we have not really explored yet in great detail. Nucleons and nuclei, we now know that there are 4, 5, 6 quark systems from the recent experiments, right? We can study them in great detail here. What can we learn from there? People have not looked at. And then there is things that we can do synergetically with EIC and LHC, including universality studies of various collisions. If you have a large project like that, there's also a large organization behind it. Really requires that each one of us is reviewing each other. So the core is sitting here. I don't expect you to read anything, but the core is sitting here. These are people from Brookhaven and Jefferson Lab mainly. And Jim Yek is the project director. He's supported by the experimental science director, the managers of the project, also accelerator advisors, and health and environmental safety advisors. So that's the core. That's the central box. The science comes on this side through my office of EIC Science Director, but also from the EPIC collaboration, the user group, and the accelerator collaboration that is being formed, how to improve the accelerator, how to build the detector, and how to do the science. Those are the three things that we coordinate on one side. But then there are other people, now that we have an international project, you see these names, these are directors of international laboratories at various places or their representatives who are then advising Brookhaven National Lab Director, who has the ultimate responsibility to realize this project for their world community. So those are the kind of structures that need to be evolved and they get formed. Yeah. So I just wanted to see how much, and then there are each sub-detector system has these kind of boxes where there are scientists working at that level and passing the information about what is possible, what is not possible, what is possible, all that kind of thing that works here. All right. think I'm going to skip that. I've already said all the things about being internationalized. Here is the movie of all the things that I mentioned to you. It was a long journey, 30 years, but I think it was completely worth it. These are all the documents that have been written about it, resulting in these final three that has made the project real. This is what we are now building. It took us 30 years to get there, but I think we're close. Only 10 to go. Here is that 10 to go. We are somewhere here. In 2025, the rig operations will stop, which means that people who want to construct various parts of the beam can now get into the tunnel and start actual construction inside the tunnel. And that's the transition point around end of next year. And that's when the construction of the EIC starts at various phases and continues. And somewhere between 2031 to 32, there will be first collisions. Those collisions will not be for me and you. Those collisions will be for understanding the machine. A new machine that comes up, the machine physicists need a year just to do their experimenting, figuring out that you're not burning, you're not dumping the beam at places you don't want to. So all these tests happen over a year. So we don't have control over that. But at the end, they seize control to start doing physics. Now, at the moment, there is an uncertainty as to where the physics will start, somewhere in FY 2032 to 34. So that's the uncertainty range where these collisions could happen, and we could do physics starting. Last, it's nice to be young and naive. Here is a slide from my 2002 slide talk, and I was wonderfully optimistic to talk about first collisions in 2011. And as I told you, I have no regrets now. And every year we were studying this and struggling through this. It was clear that we were making progress. But I was naive enough to say, put in writing, 2011, that is when we will run the first collision. I feel like that person right there now. But that's fun. Okay. In summary, I think this is electron-ion collider, a high luminosity and polarized machine funded by the DOE, will be running, probably built in this decade and operate in 30s and also 40s. I think 15 years is what we think it will run. It will address some of the most profound questions in QCD that remain unanswered. As somebody made a comment, this is the only game in town in the next 10 to 15 years. Collider, the only collider that is being built for sure, the only detector that is being built for sure, and absolutely new physics. Two hermetic detectors could be built. One is funded, the other one will need some physics case. First collisions in 2031-32, physics could start in 33-34, about 10 years from now, where most of you will have faculty positions, right? They're all grad students. You will be there. You will be leading this part. And for the career depth, so that's the last line. This is where you will actually excel. There's a lot of data that is going to come at you and a lot of problems. So, thank you very much.
We have time for questions if there are a few.
What was the deciding factor to pick the rig proposal over the JLab? Because it kind of naively seems like they both have the ingredients to make the machine.
Sorry, say again?
But what was the deciding factors to pick rig over JLab for the EIC project?
Yeah, there were a few things that were different. One is, I told you, the investment in the rig complex and the pre-injector of $2.2 billion was important. That was not there. So if you take an equivalent collider for electron beam that needed to be added, then you add the cost of the other one, becomes more than $5 to $7 billion. Yeah, that's one. Have you been to JLab?
Yeah.
Okay. How big is it?
It's not formalized.
It's not, right?
Yeah.
So it doesn't fit.
Sure.
So if you go towards the south side, now there are these restaurants and all these have come up, right? On the right hand side, do you know that there used to be an open lot where school buses used to be parked? That was the location plan. But if you look at the perimeter of that, it was so small that even with the most optimistic estimates of magnets available by 2034, you couldn't build the same energy. Remember on first day when you saw the accelerator talk, you said bulk of the energy, cost of the detector, collider comes from the dipoles. Remember? The dipoles have the strength to accelerate the beam. Yes, they do that. And if you want to build a small collider, you need the most strongest dipoles or machine elements. And he said 16 Tesla per meter is what, or Tesla meter was what is dreamed of. Yes. And the proposal that they had assumed said we will need those 16 Tesla, which would have been 20 years from now. And it's completely R&D. So then if you scale it back to what is known today, or even make it a little bit more optimistic, the center of mass range was limited. The center of mass range was between 20 GeV and 70 GeV. You couldn't go beyond. And that made the science case weaker because all the nuclear science to go to the lowest X or proton to go to the lowest X with spin, that's cut off. So I think there was a scientific reason driven by the cost, driven by the area, driven by the fact that there is a collider already. So they were very innovative. And I can tell you many of the ideas that they inserted to get to and start competing with ERIC, we have adopted, and that has made EIC better. So if you look at a lot of people, accelerator scientists who worked on that proposal are now part of the proposal for EIC. So it's not complete waste of effort on any. We actually took the best of ideas, and for that, our machine is better than what we had proposed in the first. Nobody wants to know what bow tie? Why bow tie? Now he wants to know.
I was gonna ask you later.
You will. Oh, later. Okay. So one of the things that I mentioned, emphasized as RIC is the only machine in the world that does polarized protons. And did you ask Monta as to how we get polarized protons? We spoke this morning, right? Yeah. So did he mention something called Siberian snake magnets? Yes. So Siberian snake magnets, what do they do? What do they do?
Invert the spin direction.
They invert the spin direction. So you take a dipole magnet, is a model, you hold one side and twist the other. Yeah. And then the proton, which enters vertically polarized like this, switches over, turns by 180 degrees as it comes out. That is what Siberian snake magnet does. Now, in addition to this, in the ring, which is 3.84 kilometers, there are imperfections in the ring. They're not absolutely aligned. You can never have an absolutely aligned machine. So I can tell you at RIC, at 3.4 kilometers, if you take the sum of all misalignments, sum, not individual, sum of all misalignments, it comes to about 300 microns. But 300 microns is already too much. We can sustain it for 250 GeV, get there with polarization. But what happens is because of those local misalignments, the proton comes in like this, and then it gets a jerk because it's not completely aligned. The proton polarization will go from here to, let's say, here. If you don't do anything, it goes around the thing and it will probably go another way because there are other misalignments, but comes back to it already tilted. This time goes back again, it will go this way. But if the proton was, some of the protons in that bunch were doing this to start with, they will go further in. So after a few thousand turns, all the protons will be oriented differently, correct? From where they started, which means that uniformly distribution means that unpolarized bunch emerges. That's what we call loss of polarization. If you remember, you wrote P up minus P down divided by P plus P down, right? If the difference between the P up and P minus is 0, you have an unpolarized beam. All right. Now, what does the dipole magnet I showed you or the Siberian snake do? So it comes through here first, goes through that imperfection resonance or place, and boom, it gets depolarized a little bit. Now it comes back, but there is a Siberian snake in the magnet. So now it enters the mag in that direction, the snake in that direction, it comes out with that direction, 180 degrees off. Now it goes to the same imperfection the impurity or with that alignment, it gets kicked the other way around. So over many, many thousands of turns, you're either kicking it this way and the next time you're kicking it back into position. So over time, you maintain polarization. That's called a Siberian snake magnet. It was called Siberian snake because it was discovered, invented in Siberia, the Novosibirsk lab. Accelerator scientists from there were inventive enough to figure this out. And they were implemented in RIG for the first time and maybe in IUCF, Indiana University. But if you look at the path of the proton, I'm giving you a very simple path of it. It actually looks like a snake going through. There's lots of dipole and quadrupole magnet combinations that actually does this. Not as simple as twisting the dipole magnet. And that's why it's called a Siberian snake magnet. Now, we have 4 of them at ring in each of the rings to keep the polarization to about 60%. We're going to take 2 of them from the blue ring and put them in the yellow so that we can get to 80% polarization. The more the snakes, the better it is, right? Because you're saving polarization at much faster. When you saw that ring, that bow tie, you take a circle, that's your normal ring, you hold one side and you flip the other. Now you thought, if you think about it, what was the direction of the magnetic field? In the ring, it was all in one direction. Yes, but now I hold it here. So this part is vertically up, but I flip this out here. So this time, this half is now the other way around. And it is a gradual change from this end to that end. That's exactly what a Siberian snake does. Yes, so now this was another idea from the same person who built the original snake, who now works at Jefferson Lab from Novosibirsk. He came up with that beautiful idea. Said, hey, I don't even need Siberian snakes. If I can get you this flip kind of a ring with a bow tie shape, you don't need Siberian snakes. I think it's an ingenious idea. Fantastic. It would have worked. I'm convinced it will have worked. But unfortunately, it was not large enough. I always tell them that we should build a small ring just to show that it works. It's a beautiful idea. So that's the origin of the topology of that. Yeah. How was it chosen?
Yeah, you said Hera had 300, right? But yeah,
Correct.
The years.
140 EP maximum, yes. Part of it is because we have RIC. Part of it is how much of the energy, how much of an electron beam energy you can build for the collider. So what's the maximum you can build in a reasonable nuclear physics project? And then the fact that we use the nuclei, get that 200 times enhancement in the proton density, allows us to go 1 decade below the Hera. So if you're exploring whether this low X, what is the low X behavior, this is good enough. So if we find that it doesn't work, there are 2 options. One is to propose a similar project at much higher energy at CERN. There is a concept already there called LHEC. It's about 10 times larger in center of mass energy, about 1 TeV. That's one option. Or we have thought about putting a muon beam here at RIC after the EIC. Instead of remember the muons can go to higher energy. So we can store about 200 to 400 GeV muons. And that means that we can go to about 0.8 TeV or 1 TeV again. with muon. It's a very different physics. It's way far in the future, et cetera. But if you don't find saturation, as we are looking for here, that's one option. But that's the origin of the energy.
Is that beyond the extreme?
Sorry?
Is that beyond the extreme?
Very good question. That's something that we need to work on. Yeah, the muon decays. But people have built muon experiments. We have done them in CERN. If you accelerate them, they slow down, right? I mean, the decay. Yeah, so that's why, that's the trick.
Questions now, let's,
There's a barbecue, you can come back to me downstairs.
and there's plenty of time for discussion.
Yep.
But let's thank Abe again, so. And just a reminder, the schedule will start the talks at 3:30, so we'll have a half-hour break, and then we'll, the barbecue's at 5. So we'll have a good amount of time, a little break before then, so it should be good. All right, we'll see you at 3:30.
Oh, what was the memory lane? Never took pictures.
I guess the thing is, without cell phones.
I know. But there are people who actually take
Yeah, but,
a lot of pictures.
right, yeah, but that was kind of specialty thing, right?
We were not.
Camera,
Yeah, regular.
yeah.
Actually, yesterday.
Anyway, good.
I mean, I don't even know whether there's a picture of her.
The context here, so there are some pictures there. If you take, if you just, Google one and you. There's a famous one that is portraying kind of thing, the National Academy.
Right. That's it.
No, but there are pictures that I've seen in the experimental context. Yes.
You know, something similar in your
Yes,
presentation.
yes.
So the quantity you actually care about is delta G, right? That's
That's one of the things, yes. That's the same one that I should.
right. Why did we multiply by X? I guess.
So what is important is not the structure function itself, it's the area under it. That control, that's the contribution of that structure function or that.
You were not at my lecture yesterday.
I was, but I did not follow.
So you remember, I kept saying you plot on a log scale, but you plot X times PDF in such a way that the area.
But right, the barbecue.
So what is going on here is that this is the uncertainty.
Yeah.
And if you just simply look at the X times delta G, that is the area under the curve. That
Because it's
contributes
right,
to
it's on a log scale.
Now,
Plotted G on a log scale, then the area is not
can eat the whole thing and I.
the X, and that's the
Where we have like.
measure, I mean, the protein having
Yeah, you gotta, there's half of a pizza.
E log X, X.
So this is.
So it's G is a function of X. And you want the integral, so you have to integrate. So basically it's G,
I would do the.
dx integral over X. That's X times delta G.
So that's the reason why when you plot the PDFs, you always
Just put it on for like a minute or two.
plot on a log scale because you
Okay, before or after here.
you plot on a linear scale, this would all be squeezed. But it's
It's like, it's like a bunch of smart.
But then if you plot on a log scale,
It sounds kind of good.
area under the curve is no longer a number. It's not multiplied by X.
You need a lot of.
This is effectively the integral. This is what we care about.
Correct,
Yeah.
yes.
Well, it's not the integral, it's
It's
the
the-
thing such that the area under the curve. The area under this curve is the it's the total number.
Yeah.
Okay.
Or, yeah.
Total area under this curve for any PDF is the total number of parts.
Yeah, I think that makes sense. But when, so probably an naive question, but when you integrate a function,
Let's say we
say,
do
a delta function of X,
or
you
next round.
just don't pop out an X, but you have to think of the functional form of delta G, right?
So, yeah, I mean, the stuff you're interested in is the integral, that's the G.
Yeah, yeah.
I'm not.
But
saying
then you want
something
also
everything.
to see visually.
No, no, it's not
area.
like half, like. one.
And you know, the integral under a curve would be,
Huge range.
integral would be the area under the curve. You plot it this on the linear.
Don't say I have.
Because you plot it on a log scale, you know, you stretch the small x region all the way to infinity.
Yeah.
And then you need an extra factor of x to suppress this, otherwise you get infinity.
Yeah.
Okay. So you're saying this X is basically a compression factor and then.
The x is a compression factor such that even though you're plotting a log scale, the
Okay.
area under the curve
Curve is
is
fine.
still the integral from 0 to 1.
Okay. Right, that makes.
I mean, you try and write the integral over the integral delta g integrated with respect of log x rather than x, which is what you do when you plot like this.
Okay.
D log x is x dx.
Yeah.
So that x is the x that people can
Okay.
take up for everything.
Thanks.
All right. Water.
Yeah, so it was nice because there were, I mean, many.
I don't know.
नहीं चलाई है बंद किया है हमारे वहाँ हाँ हाँ तो मैं ड्यूटी में देखो एक हमारे स्क्रीन से जो डेटा ले रहे होते मॉनिटरिंग हो रहा होता है वहाँ एक ठीक है वो मॉनिटरिंग के लिए मॉनिटर तो वो जब कभी करोगी ना जब चलाओगे
आप कौन से फेयर दिए थे ग्रुप वाले
जापान
कौन से क्या
फेयर में तो अब स्टार्ट
जापान में कौन सा एक्सपेरिमेंट है
स्प्रिंगेट में नहीं थी स्प्रिंगेट फैसिलिटी में थी
8
मैंने तो बनाया था
अरे वाह
तो उसका डेटा टेकिंग और टेस्टिंग मजा आती है यार पता है, 4 दिन बिना खाए पिए बस भाग भाग के खाना खाओ टाइम वेस्ट नहीं करना पूरी रात का किया तो मजा आ गई
स्प्रिंग 8 EIGHT
स्प्रिंग
हाँ।
-8 कोई लगाता है कोई नहीं लगाता है इसमें मेरे को तो पासवर्ड है क्या पता एक नया टाइप का प्रोटोटाइप बनाना था डिटेक्टर भी टाइम के साथ वो होते हैं बेटर एफिशिएंसी डिटेक्टर का टाइम और टाइम रेजोल्यूशन अच्छा होना चाहिए तभी तो वो पार्टिकल को ट्रैक
जब मैं ढूंढ के लोगों को ऐसा स्पेलिंग गलत लिखना
SPRING एक्सपेरिमेंटल फैसिलिटी है वो
तो आप इन चीज में जो काम करते हो रिसर्च साइंटिस्ट होते हैं जैसे हमारे इंडिया में वेक सिस्टम है बीसीसी है तो आप उसमें रिसर्च साइंटिस्ट प्रोफेसर भी इन्वॉल्व होते हैं कम होते हैं तो आप जब यहाँ पे जापान में गए तो वहाँ पे रिसर्च साइंटिस्ट थे प्रोफेसर थे
country vary करते people do not hand over the things that in the hands of the student they to guide you कुछ भी नहीं आता था हंसते रहते थे वो लोग मेरे पे किसको कुछ आता ही नहीं मैंने किया नहीं है तो क्यों
तो
आएगा?
यार शुरू में क्या है? 1 महीने 2
मैंने कहा मैंने
तीसरे महीने
छुआ भी नहीं है, मैंने अपने घर में चाकू भी नहीं उठाई है। मेरे को टेबल बनाने को बोल दिया उन्होंने, पकड़ा दिए लोहे वोहे रेंच वेंच के, तो चलो टेबल बनाओ। इतना ठंडा होता है यार, इतना ठंडा होता है वहां पे -3 डिग्रीज पे सभी टेबल।
अरे ना प्रॉपर सूट वगैरह पहन के जाते हो जिससे वो
गर्मी लगती थी, कितनी पहन के आ रही है,
You already know the answer.
पहन के काम कैसे करोगी?
Which word?
The it's cheese, but it's like different multiple cheese.
नहीं यार यहाँ लेकिन मुझे सही लगा यहाँ का।
Yeah. It's like so I got like just like plain cheese yesterday. I had to do like a little slightly different, but I wanted the same thing.
So I got the wings there last night.
So they're pretty good. I really don't like chicken.
यहाँ भारी है ना।
Oh no! And I had the chicken parm sandwich 2 nights in a row. Yeah, I don't.
And then you're gonna keep talking about it like, that sound good.
No. I definitely my least. I can't say my least favorite food about Domino's. I like quite a few things, but I don't like the chicken. Sure. Have you ever had the pasta? No, I'm scared of it. Okay.
I'm just curious. I need an expert opinion. What's your dollars? What are you done right?
I'm gonna be like on the verge of tears, like on Monday. My body will finally think I'm free from Domino's and then come right back.
Thanks, it's so cute. Really cute. And I think they can rewrite it like chicken noodle some as kind of.
I'm scared if I sleep in my own bed tomorrow night, like what I'm gonna do.
Like, yeah.
Okay, I was gonna. Oh, you're here? I didn't see
Yeah,
you.
but they introduced another one. Anyway, in the end, they can find. I have derivatives in the first. I can show you.
Actually, last time I could give you a white.
Focus square equal to S.
Like that.
Okay.
I understand. So I gonna do barbecue or you do one thing, but do it well. Can't do both.
All right, yeah.
Other one. You
Why?
decide. So you want-
I see why
Without-
will be.
Without being penalized, either.
I think why it will be fixed. They are arguing. Because you have always studied ethics. Why is related? And you try to.
Well, we don't need different religion. You can basically the momentum. It's, yeah. Yeah, there's no loss in it. Right?
Your picture is when you increase the energy, you will have like more
Did you? The structure
in the system. Rather than the size.
big
This
and basically almost like that. That's the fixed pattern.
yeah, so. Right, yeah, he is on time. Balance. That's different from this.
It's not accurate.
I don't want it means he's on bleeding, the part of evolution, part of bleeding, because the parts can come. And the gluon can like come back to the parts. He's saying this, but that's not this. That's different from this. This discussion is that, so you just think about hacking. So if your enemy is not large enough, it's fast to have a large size. But when you increase it, and the number of gluons are also increasing. But you only have gluons with smaller size.
It's the polarization.
That just pack
Same.
system.
Same.
They can fit, they can fill in the gap.
Yeah,
And
the reverse, and then that's what
the
it is.
picture is when you increase the energy, you can have a more random ones.
No, we can, the collision area, we know exactly how they come in. And we
So
can
we
manipulate.
know whether.
Saturation. So the is meaning of, so the saturation
We control it.
does not mean the number of ions of improving.
Right.
What it means that the
Electrical
ions
ions,
outside larger
I don't know what the
values
spin is.
saturated. Just means
It plays
the
no
large size is saturated. The larger size is saturated.
PDF.
Yeah, that means.
Oh, yeah, we control that. You can tell me what you
So
want
what
and I
if
can
it is
give.
happening like this
Yeah.
or like this?
Yeah, we control it. Follow some-
Yeah, I'm thinking about kinetic.
Not every
I'm thinking about this.
one of the. Like,
But we have 70% population, and 70%. They all move in that. All move in this direction, they all move in that direction. All move in that. No, this is not about deformation. of the foot.
I understood that, but
Deformation of the foot.
The thing is, countermeasure.
Yeah.
Okay, sorry.
Oh. Nothing here. That's very easy.
Sorry to interrupt briefly. We're on a brief break. Sorry about this. Alexei was out today, so I'm by myself at the CTech school. But just glancing at the proposal, should I try to, put some words in the phenomenon section quick too, or is somebody else going to do that? I don't want to overlap.
That's what we do. Spin rotator, right? Half a snake. And it goes from there, to there. Half a snake. Instead of doing that, doing that.
the second.
Sorry, not the second. Just cut the spin, the rotation, the Siberian snake into half. Instead of 180, it goes 90. Then we have longitude. The other half, then it will go, this will go that way and that will go that way. Flip the spin.
Yeah, that sounds good. And I'll sort of follow along the
Yes.
comments that I had before, if that's okay. And again, feel free to tweak
Because
those.
measure.
I will aim for getting something tomorrow. I have the weekend free, so that sounds good. So, thank you.
Now,
Okay.
20 years, I can tell you,
Right.
measure.
I'll be off, but I'll for the email and catch you guys later. So apologize for the delay. Bye.
No, contribution of what? We can't say.
Yeah, I think it's people suggesting.
Quark, anti-quark together, anti-quark student. Together, it's 23%. Two of themselves, another 5%. That's what we have measured. The rest has to come, we have not measured it, but the rest has to come from orbital transfers.